Okay, let's do a little practice. So let's just worry about, let's find critical numbers. If you want to find the critical number of this, again, you're going to have to do your own derivatives because I'm not teaching that in this chapter. So the derivative of this would be 9x squared minus 36x. So I would set that derivative equal to 0, and then I would factor out a 9x out of each term, and so I get 9x times x minus 4. And I know if you set 9x equal to 0, you would get x equals 0. And if you set x minus 4 equal to 0, you would get x equal 4. So x equals 0 and 4 are the critical numbers of this function. Okay, here's a rational function, x over x squared plus 1. So apply your quotient rule and see if you can get this derivative. Now, the first thing I'm going to do is find out what's going to make the derivative equal to 0. Well, the derivative would be 0 if the numerator is 0. And if the only thing that makes the numerator 0 would be if x minus 1 equals 0. Well, that means x would be 1. Or if x plus 1 equals 0, which means x equals negative 1. Now, x squared plus 1 quantity squared, well, x squared plus 1 can't be 0, so there's no places for this function to be undefined. So the derivative cannot be undefined, so therefore the only critical numbers you get here are the numbers you get by setting the derivative equal to 0. Alright, let's take a look at a couple more. Okay, this one up here, x times the square root of x plus 1, you probably want to write that square root as x plus 1 to the 1/2. And then to get the derivative of this, you need to apply the product rule and then simplify it. So remember the product rule, you take this times the derivative of this and then plus this function times the derivative of x. But that's the product rule. So do the product rule and then get the derivative, and this is what you should get. Now, when I get this, I set it equal to 0. The only way that this can be 0 is if 3x plus 2 equals 0. So if you set 3x plus 2 equal to 0, that's the numerator, and you solve that, you'll get x equal negative 2/3. Now the only way it can be undefined is if the denominator can be 0. So you would set 2 times the square root of x plus 1 equal to 0 and figure out what makes this a true statement. And the only number that would make this 0 would be x equal negative 1. And just, you can solve that equation algebraically. Just divide both sides by 2 to get rid of the 2, and then you can square both sides and then subtract 1, and you'll get negative 1. Now, let's talk about why the two make it our critical numbers. Negative 2/3 is a critical number because it makes the derivative equal 0. And negative 1 is a critical number because it makes the derivative undefined. Now, if you remember that problem earlier, I said there was a number earlier that made a derivative undefined, but I said it wasn't a critical number because it wasn't in the domain, or the function wasn't defined there. But if you actually plug negative 1 back into this function, you actually would get negative 1 times the square root of 0, which would just be 0. So negative 1 is in the domain of this function, so therefore negative 1 can be a critical number. Okay, let's look at the next one. Okay, so here we have the cube root of x squared minus 1. Now you can rewrite that as x squared minus 1 to the 1/3 power, and then you just use the general power rule to take the derivative of this. Don't forget, you bring the 1/3 down, then you change this to the negative 2/3, and then remember to multiply by the derivative of the inside. That's where the 2x comes from. So anyway, I get 2x over 3 times x squared minus 1 to the 2/3. Well, the first thing I do is say, well, what's going to make this derivative 0? Well, the only way it can be 0 is if 2x equals 0. And the solution to 2x equals 0 is x equals 0. And then I say, well, what will make the denominator 0? In other words, what will make the derivative undefined? Well, the only way the derivative can be undefined is if I can figure out what makes 3 times x squared minus 1 to the 2/3 power equals 0. Well, actually, if you do a little bit of algebra here, you can divide both sides by 3, and that'll get rid of the 3. And then if you raise both sides to the 3/2 power, well, on the right-hand side, 0 to any power is just 0. But by raising all of this to the 3/2 power, it'll actually eliminate the exponent, and you'll just get x squared minus 1 equals 0. And I think you know how to solve this. Just factor that into x plus 1, x minus 1, and then you'll get the solution to that is -1 and 1. So you got 3 critical numbers this time. 0 is a critical number because it makes the derivative 0, and plus or minus 1 are critical numbers because it makes the derivative undefined. I invite you to graph all 4 of these functions and investigate what's happening at the points of these critical numbers. But on here, I just went ahead and did the last one. So let's look at the graph. This graph looks like this. It kind of bends down here, and then it kind of goes vertical there, and then it turns here and then flattens out kind of there, and then it goes vertical again over here. Well, if you'll notice, you had critical numbers at -1, which is actually what you have right here. This point right here is -1, and remember the derivative was undefined at -1. Now, I told you a while ago that the derivative could be undefined at a sharp corner, but the derivative can also be undefined where you have a vertical tangent line. So for this problem, at -1 you get a vertical tangent line, and of course you know vertical lines have no slope, so that's why the derivative is undefined at -1. Same thing happens over here at +1. You get that vertical tangent line, and therefore, so that's why the derivative is undefined at -1 and 1, because the slope of the tangent line is vertical. Now, at 0, remember at 0, this function, the derivative was 0. So at 0, notice how the graph sort of flattens out here, and you get a horizontal tangent line. So the slope of the graph at 0 is actually 0. And so it's good to investigate these to see this action. Now, what I want to talk about now is how do we test for whether a function is increasing or decreasing. I've already given you a hint, but basically what you do is you determine where the derivative is positive. Excuse me. Where the derivative is positive, then the function is increasing. And then determine where the derivative is negative. Wherever the derivative is negative, the function must be decreasing. And if the derivative is 0 over an interval, then the function is constant. And again, I told you before, we probably won't see a lot of that. So to apply this test, you find the derivative, you identify the critical numbers, and then those critical numbers will set up some test intervals for you to test, and then you test the sign of the derivative in each interval, and you use the test to determine if the function is increasing or decreasing. So let me show you how we can do that. Okay, example 1. First step, find the derivative. Here's the derivative, 6x squared minus 18x. Step 2, identify the critical numbers. So set it equal to 0 and solve it. Now I'll leave you to do the algebra here, but I found that if x is 0 or if x is 3, then the derivative is going to equal 0. So these are the 2 critical numbers. And then I want to test intervals. So right here what I did is I basically took the number line, or the x-axis, and I'm going to break the x-axis up at these values. So here I'm going to break the x-axis up at 0 and 3. So this vertical line represents x equals 0. This vertical line represents x equals 3. And then that's going to divide the x-axis up into 3 intervals. Everything to the left of 0, negative into 0, everything between 0 and 3, and then everything to the right of 3, 3 to infinity. Then I'm going to pick a test point here. So pick a test point. I'm going to call those k. So the k I chose in here, -1. I need a point between 0 and 3 here, so I'm going to choose 1. And I need a point greater than 3, so I'm going to choose 4. Now, the test point is to plug back into the derivative. So evaluate the derivative at -1. So go back up here and plug in -1 and see what the sign of the derivative is. So if you plug -1 in, you're going to get 6 plus 18, which is positive. So the derivative is positive, therefore we know the function is increasing over this interval. In this interval, the test point is 1. If you plug 1 in, you get 6 minus 18, which is negative. So the derivative is negative, therefore f is decreasing on this interval. And then when you test this interval, you can plug 4 in, and if you plug 4 in, you're going to get 6 times 16 minus 18 times 4, and you'll check that and you'll see that that's positive. So since it's positive, the function is increasing on that interval. So in summarizing, the function is increasing on the interval negative infinity to 0 and 3 to infinity, and the function is decreasing on the interval 0 to 3. And you can graph this function to verify your results. Okay, I'm going to leave you to do example 2 for practice. So freeze the video, see if you can do example 2 just like I did the first example. It's very similar because they're both polynomials, so they work pretty much the same way. You just get different critical numbers. And when you're done, you can go ahead and restart the video and move on. All right, let's take a look at one that's a little stranger. This function here, if we take the derivative of this, we're going to get this expression, 4x over 3 times x squared minus 4 to the 1/3 power. Well, if you set that equal to 0, it equals 0 when x is 0. And if you find out when the derivative is undefined, it's actually undefined when x is plus or minus 2. So those are the 3 critical numbers. So if you look at the table now, you'll see that I'm breaking the x-axis up into 4 intervals. At -2, it breaks it up to everything less than -2. And then I have 0, so I have everything between -2 and 0. And then I have 0 and 2 is the next critical number, so I've got everything but from 0 to 2. And then the final one is everything from 2 to infinity. Okay, so now let's pick some test numbers in here. So -3 is less than -2, so let's plug -3 into this function. So if I plug -3 in, the top's going to be negative, the bottom's going to be, 3 is going to be positive, so that's not going to change anything. The bottom's -3 minus 4, which is 5 to the 1/3, that just means the cube root. Well, the cube root of 5 is positive. So I have a negative on top, a positive on bottom, negative divided by positive is negative. So in this interval, the derivative is negative, therefore the function must be decreasing. So in the next interval, I'm going to test -1. So if I plug -1 on top, I'm going to get a negative on top. On bottom, if you plug -1 in here, you're going to get 1 minus 4, which is negative, and the cube root of a negative number is negative. So here you're going to get a negative over a negative, which is positive, so the derivative here must be positive in this interval. So the derivative is positive from -2 to 0, so that means f is increasing. And then on the next interval, plug 1 in, and I get a positive on top. 4 times 1 is positive. And if you plug 1 in here, you're still going to get a negative inside here, and the cube root of a negative is negative. So positive over negative is negative, so the derivative is negative on this interval, and so the function must be decreasing. And then finally, the last interval, I'm going to use a test number of 3, and when I plug 3 in, I'm going to get a positive on top, and you can plug 3 in the bottom and see that you get a positive on bottom. So positive divided by positive is positive, so therefore the derivative is positive on the interval from 2 to infinity, so it's increasing. And then you summarize the results. F is increasing on the intervals -2 to 0 and 2 to infinity, and then the function is decreasing on -infinity to -2 union 0 to 2. And I'll do some more examples for you in another video.